In the late 1990s, astrophysicists noticed something strange. The galaxies were actively rushing away from us, accelerating into an expanding dark void. To explain this acceleration, theorists turned to a mathematical slot in Albert Einstein's theory of gravity called the cosmological constant. This became the foundation of what we call the lambda CDM model. The math rests on a specific premise that the otherwise empty vacuum of space possesses an inherent, unchanging energy. As space expands, more of this vacuum energy is created, pushing everything away at a steady, uniform rate. If that energy density stays exactly the same forever, the universe has a guaranteed fate. The push will eventually separate every particle from all the others, crossing unbridgeable gulfs until the cosmos goes completely dark and cold. But the observational data holding up that entire theoretical framework was relatively low resolution. The picture we had of the universe was a bit blurry. Our accepted timeline for the end of the universe was essentially a well-supported guess, resting completely on a theoretical constant. To know for sure, we needed a sharper map. That sharper map arrived courtesy of two enormous modern observatories, the Dark Energy Survey in Chile and the Dark Energy Spectroscopic Instrument, or DESI, sitting high on the Kitt Peak Ridge in Arizona. The hardware behind DESI is massive. It uses an array of 5,000 swiveling robotic eyes, snapping into position night after night to collect the light from nearly 15 million distinct galaxies. Researchers analyze how ancient galaxies group into spherical shells, leftover ripples from a dense early universe. Because these shells have a predictable size, they act like a ruler. Measuring them lets scientists rebuild a frame-by-frame history of cosmic expansion over 11 billion years. Plotting 15 million coordinates transforms the map into a high-resolution time machine. It allows us to see exactly how gravity and expansion have battled it out over eons, putting our standard physical laws to a rigid test. After 3 years of collecting and processing all those light signals, the DESI collaboration met in Cancun, Mexico in December 2024 to finally unblind their dataset. In a vacuum, you could still interpret the paths of those 15 million galaxies to fit Einstein's standard constant. But the tension arose because scientists combined their high-resolution galaxy map with other established readings of the cosmos, starting with this oval-shaped map of the cosmic microwave background, which shows the temperature fluctuations of ancient light. They also folded in thousands of known historical markers from deep space, using the exact locations of distant supernovae. This graph shows all the datasets merged. If dark energy were constant, the points would follow a straight line. Instead, observations curve sharply away. This gap is 4.2 sigma, a 1 in 30,000 chance of occurring if the standard model is right. This analysis points to a significant tension with the standard cosmological constant. If the trend holds, it suggests that dark energy isn't stable and the engine pushing the cosmos outward is losing steam. If the energy in the vacuum of space is evolving, there is a serious problem for theoretical physics. It means the cosmos must contain an extra, totally undiscovered ingredient. That missing piece might be a subtle, previously undetected quantum particle acting like a thinning fluid, or it might point to a flaw in how we calculate gravity on a massive scale. This tension has split the physics community. String theorists argue that vacuum energy naturally dissipates over time in their mathematical models, while skeptics point out that the known laws of particle physics demand a steady, unchanging vacuum energy. Because dark energy appears to be weakening, the cold, dark doom of eternal expansion is no longer guaranteed. If the outward push fades enough, gravity could take over and force everything to reverse course, crushing the entire universe back into a central point. For nearly 3 decades, we thought we knew exactly how our universe worked and how it would die. We built the sharpest map in history to confirm that destiny, and instead we found evidence that contradicts our basic assumptions about the vacuum of space.